Yes, sir, it's visible.
All right. Okay. All right. Okay. Okay. So today we'll study block cipher mode of operation. And of course, again, I have taken this from lovely presentation and the book published by Berkeley. So I am still taking content from the same place because this is the best that I could find. Okay. All right. So far we know. So where are we now? We are in symmetric key encryption, and we know that there are two types of instruction: symmetric key and asymmetric key. In symmetric key, both keys that we use for encryption and decryption, okay, the key that Alice uses or Bob uses, both are the same. Okay, these steps we know. Okay, and then we have studied also about the one-time pad and IND CPI capability, and we know that one-time pad, because they change keys every time, so they are IND CPA secure. Okay, so keys are never used, but that's not really practical system because you cannot generate keys every time. Okay, because Alice and Bob are communicating, so they are communicating, but every communication or every part of the dialogue cannot have different keys. Okay, so there's a restriction. And however, this gives a lovely model, because this is absolutely secure, confidential. Okay, now then we have studied concept of block ciphers. Now in block ciphers, the concept is that encryption and decryption is on fixed size blocks of bits, right? So here is n bits of a block of n bits, and so this is encrypted. So it means that n bit blocks, one block of n bit is encrypted, and then there is a key, and then we get output also, which is also again of n bits. So input and output both are of same size, which is a block, and same way we do decryption. Okay, so we have studied all this. All right, and we have found out that we have studied correctness, efficiency, and security. Of course, we have looked at how DES and AES. So DES came early, and which had the block size of 64 and key size of 56. It remained in use for a very long time, and then now, as speed of computers is increasing, it's easy to break it. And this algorithm remain unbroken for 40 years, but now people have found out that they can break it because the key size is small. Of course, it requires a lot of churning of data. Now this churning of data is based on the key. Okay, and this churning operation is essentially shifting, substituting, and moving between various rows and so on, right? Okay, so if you are interested, you can go through the paper and find out more details. This is more of theoretical research, and I mean, you're really interested, how does it work? Please go through it. Now note that all this is deterministic. Okay, all right. So then we came up with AES, advanced encryption standard, wherein key size is 128. Okay, of course, now we use 256-bit keys. Okay, and the block size is also 128. And we have seen again, it has similar to DES. Now this churning, movement, substitution, all is designed differently. Okay, and now this is standard. So you can download, for example, you are using your message M, you are encrypting with AES. This AES library you have downloaded from some source. Okay, and your friend wants to decrypt this message, which is C after encryption. Then they can download not necessarily this AES algorithm from same source. It can download from some other source. So there's advantage of standards. So any company can make algorithms or actually implement those standards, but it should work the same. Like in networking, you have seen, right? So your machine uses TCP stack, server also uses TCP stack. Not necessarily these TCP stacks are designed by same company. Once standards are there, then everything has to, the way a protocol behaves has to be the same. Okay. All right, you would have studied that in network. Networking is nothing but is a protocol. Same set of understanding is there, both recipient, receiver, and then same state machine they have for that exchange. Okay, while implementation could be by anybody. So we are here in the block ciphers. Okay, and stream ciphers also we have studied. Now the question is that we have just seen 128-bit block, and we encrypt it using this encryption using a key, which we also say 128, and what we get is also 128-bit encrypted message, right? But is it practical? Is it practical? No, it's not practical. We can use this method, right? AES is of course used, but AES by itself cannot be used. So it has to go along with some other functionalities. And what are those functionalities? First thing you notice that when we say 128-bit block, the message which you want to send to somebody else, or Alice wants to send to somebody else, cannot be always 128-bit. It can be more or it could be less. Then what is to be done? So that's one problem that we need to fix. Okay. Second problem is that what we have seen is that if you use the same key, then it is not enough secure, right? It's not secure enough. It does not have IND CPA capability that we have studied earlier, right? Or one-time pad equivalent. Sorry, let's not go back. Okay. Okay, so now that's the second problem, right? It means that if you use the same key and if the contents are very similar, suppose we are parsing a message or sending a message, okay, and then we encrypt it through this. Now image hardly changes. In general, parts of the image remain the same. Okay, so now when we encrypt it using this algorithm, it's a very simple algorithm, it may reveal something. So we need to do multiple things. First thing is that something to do with padding, also something to do with improving, such that it becomes more secure. Now we'll do it step by step. And third thing we may also do is that we'll have to see that how can we make it efficient. Okay, these three things we want to now focus on. All right, so these are the modes: ECB, CBC, CTR, and there are others, right? We have taken just three. These are actually the ways you can use AES encryption. Okay. All right, so modes of operation is essentially the way you can use AES. Okay. So motivation is the same. We can't just let block cipher run of its own. Like AES, we have seen 128-bit message block size. We cannot do it of its own. If message size is more than that, right? So we have defined a larger mode of operation. Essentially, some more algorithm where AES can be part of it. Okay. And with this point, we have already seen that AES by itself cannot be IND CPA secure. Okay. So somehow we'll have to include something such that it becomes IND CPA secure. So we'll do it in step by step, right? So consider this a scratchpad or the design that we are doing towards CTC. Okay, CTR, sorry. Okay, all right. So now first we'll have to move towards the first ECB mode. we'll have to improve this method. So first is that we have to 128-bit message, and here is AES block, and it can encrypt only 128-bit message, right? So now there is a limitation, as we have just discussed earlier. Now suppose we have to encrypt 256 bits, then what can we do? Simple thing is that use AES twice. Okay, so this become 256. But since we can work on 128 bits at a time, so it take first 128 bit, encrypt it, use the key, and you get ciphertext. All right, similarly for remaining 128 bits, you do encryption and this ciphertext, and the overall this the ciphertext. Any question? No? All right. Simple? Oh, okay. So this, all right. So this is what we have done. Use it twice. This is 128 bit of message, this second 120 of message, and then you get the result here. But do you notice something here? What do you notice? First, of course, the message size has to be 256. That's first thing you notice. What is the other thing you notice? Other thing you notice is that we are using the same key. Okay, so basically we cannot change the key, right? Every time. Okay, and this use of the same key on different parts of the message will reveal something. Okay, all right. So now this way of working, where we split the message into number of blocks and encrypt it and create the output, like split here message into multiple parts, for example here 3, and encrypt using same key, then we get this output. This we call ECB, electronic code mode. This is very simple, but still it has problems. For example, if what happens if message size is bigger than multiples of 128, this could be a problem. And then there is we are using the same key. There's a second problem that we see. All right, so this is the method that's described. So basically what you get output is nothing but concatenation, or just combine them and you get the result. So first split the message into number of messages blocks, okay, and then encrypt them, and then output you just combine, but you're using the same key. Okay, now you know that everything is deterministic here, and you do the reverse process, you get the original text. All right, okay, because we are using the same key, then it leaks information in some way, while it's not visible to you. But if you have a very large size message or image, then you can see it's leaking some information. Okay, for example, this is input. When we say this is a file, it could be any file, JPEG file, or it could be a .png file or something like that. Okay, and when we say, then we let's see how for example, PNG file actually describes any image, right? See, note that in computer everything is zeros and ones. So when we define a file, those of you who have done OS course, I think almost everybody would have done, and we have seen what is the contents of any file, right? So there is of course something in between is preamble or header, which is not visible to you. Okay, this is again zeros and ones, but certain number of bits, and then we define the syntax. The whole, for example, PNG file defines syntax in which bits here can be interpreted and stored. Well, all right, so this is nothing but a file that represents penguin. All right, now when we encrypt this using ECB mode, right, it will look something like this. While it's not giving all the information here, for example, what color this is, and this is dark black, this is white, and all that. But here also you can make out it's a penguin. Lot of information is done, but there is a redundancy in data that reveals, and we are using same encryption algorithm. It reveals certain things. Okay, any question?
No, sir.
All right. So now what we can do, we need to do something to improve on this. So we are now trying to add randomness. Okay, so that some randomness comes in the whole. Now we don't want to change the key because changing key is not an option. Because both sender and receiver, Alice and Bob, has the same key. So we must do something else. Okay. Okay, all right. So we are now adding randomness to the whole game, and we call it CBC mode, Cipher blockchaining mode. Okay. Now this is a popular mode for commercial applications. All right, it means that it's in use. And so now it has to add randomness, and in order to do that, it ensures that ensure blocks incorporate more than the just plain text to mask relationship between the blocks. Right here, there is some relationship between the blocks. Right. That's the reason we are getting this kind of. There is a if you code this in this file, you can see and take 128 bits blocks, for example, this block and the next block and so on, then you can see there is some relationship in data, right? And we need to mask that relationship between these kind of texts, okay, which is part of the data. So now what we can do, we'll have to introduce some randomness in that input. Now you cannot change this, right? This is part of the message that you are encrypting it. So you'll have to think of some other way. Okay. So now what we use is something called initialization vector. Okay, and the first one here, for this one we have initialization vector which you call it C0. C of course stands for ciphertext, right? Anyway, so we say initial. So we define C0 is initial IV, which is initialization vector. And this initialization vector, which the randomness that we are adding to input, is randomly generated, or is like nonce. Note that we have studied nonce when we studying architecture. Okay. So now what we can do is that we have this initialization vector which is chosen randomly. Okay, which we call it IV. So we take the first message, first part of the message, which is M1, assuming that M1, M2, and so on. Let's say that's M3 constitute main message, main text, right, or plain text that we want to encrypt. Okay, so now you apply this initialization vector to the first block, and do exclusive OR of that. Now this output you encrypt using the key, and you get the ciphertext. All right, lovely. What's the issue here?
To get back plain text, receiver must know initialization vector.
Yeah, so basically, no, this IV vector will be known at decryption time, so decryption can happen. But note that we have added randomness only to this block. There's no randomness here, right? And then if you have to do same initialization vector, then there is no randomness. So basically, all three blocks have similar mechanism. Okay, and you cannot add different vector here, because now, whatever vectors you are adding, you have to communicate it to Bob, so that Bob can decrypt it. So that's not possibility, right? So we need to be smarter here. Okay. So here we are. So what we can do is that we can take the output from here, because now this is non-determinate. So basically we have added some randomness here. So this also has some randomness, and then we can give as an input to second block. So take second block here, and then exclusive OR with output of this. Okay, and similarly take it something from here and exclusive OR here. Okay, so this is the way. All right, lovely. Okay, so this we call it CBC mode. When you take use initialization vector exclusive OR with the first block, whatever output you get, find this output, and then take that output and use this as a randomization input, and then exclusive OR with this plain text and so on. And similarly here. Okay, so we can see that C0, this is called C0. C0 is exclusive OR with, which is IV. Now, so we have CI, Cipher C1, for example, which is exclusive OR of M1 and C0. You do, and this is here, and then use the key and get the one here. Okay, so it's explained here. You take, now here I'm showing this instead of M1. So P1, P2, P3 are part of the message, which are of size B, or we can define it size N. Sometimes you find a size N. So let's assume B. So do exclusive OR of P1 with IV. This becomes input to Cipher block, or Cipher encryption algorithm. Use the key and take the output, and then use this output for doing exclusive OR for P2 and get the output here by encryption, normal AES encryption method, and so on. So what we get is that for P1, P2, P3, C1, C2, C3. Now something that I want to communicate, or something that Alice wants to communicate to Bob, will not be only C1, C2, C3 concatenated. Okay, it has to also send IV. Because once IV is known to Alice, only then she can do the reverse process. Okay, all right. Okay, so decryption is exactly like similar, right? So now IV, once Bob receives IV. Okay, so Alice is sending it to Bob. So Bob will receive what? Bob will receive IV initialization vector C1, C2, C3 in this form, right? Concatenation form. So Bob will take out IV because Bob knows what is the size of IV, which is same as size of the first block, which is 128 bits. So it takes out 128 bits out of it, and then do the reverse process, right? So Bob takes C1, encrypt it using decrypt it using key. Now key Bob of course knows, and that he will get a output of this, and which he will do exclusive OR with initialization vector. So he'll get P1. Okay, similarly for C2, we'll take C2 and then do decryption, and then take this C1. Okay, because C1 is available, it's a part of the message it has received. So take this C1, okay, and exclusive OR with what decrypted value he receives here, and then exclusive OR get P2 and so on. Is it okay? Is it fine? Any question?
So the eavesdropper will also have initialization vector in C1, C2, C3.
Yeah.
Then if only we still have only thing hidden is key, right?
Yeah, of course. But why are we doing IV?
Okay, so means it will not be able to match the patterns because we are even though we are using the same key.
Yes.
Okay.
So IV is known, but of course, you are very right. Actually, I mean, Eve also receives it, right? Very good. And Eve will use that, and we can see the pattern. If can she see the pattern?
I don't think in this case because we are using IV, so C1 would be a little different from what is generated from the key itself.
Yeah. So until she decrypts, she cannot see the pattern, right?
Yes, sir.
All right. So even if Eve receives IV, until she has a key, and she cannot see the pattern because randomization has happened, right? So she cannot see the pattern. Think about it. Because in order to see pattern, she has to apply the key first, decrypt. Because the output she receives, what will she think about it? What will she do with IV? Okay, let's assume that she has, of course, IV. Then she applies the key, some key, and then add to that IV. Exclusive OR is IV, right? So having IV alone does not solve any purpose because output is encrypted enough, right? And she has to do, then what do you call the exhaustive, uh, breaking. I mean, take all values of key and then so on, right? Okay. So decryption is exactly similar. And these steps, you can see that you can get original message back. Definition of, so we can follow this one, right? This is a definition of encryption. CI is equal to EK, where K is the key, and we are using some encryption method, which let's assume AES. And then take inputs first block, and for that you use IV in the beginning. So it becomes C0. C0 is nothing but IV. And then for decryption, you use this as input. Okay. And whatever you receive, okay. So after decryption of that, you receive this one. And then you exclusive OR with the input that is for randomization, right? So IV in the first case, and later on, earlier ciphertext, and then you do this exclusive OR, you get original MI. Okay, right? So this is simple. So now let's look at now the question is that can this be parallelized? Now we have done the splitting, right? Can we parallelize all this? No, because we'll have to wait until this output is available in the first block. Okay, so no, it cannot be parallelized because we'll have to wait for the result. Now encryption cannot be parallelized. Can decryption be parallelized? Look at here. Now this thing will require what? Let's come to the first thing. So ciphertext is available, key is available, IV is available. So this can be done in timestamp, say time period T1. Look at the second block. This is available, key is available. Okay, is ciphertext, this ciphertext also available?
Yes.
It's also available, right? So same time decryption can be done. So then same time stamp, same time period, all this decryption can be done. So decryption can be parallelized. The next thing that you can ask is how can we parallelize also input? Encryption. If encryption we parallelize, then algorithm becomes more efficient. So we'll work towards that, right? Before that, we'll go into padding. Okay, now still we are assuming that original message is multiple of 128 bits, right? Such that we can split this into multiple pieces or blocks. But that's not the case if message size can be bigger or smaller. Okay. Now we are not going to go into padding scheme because you would have studied that in networking. A similar problem is solved in networking, right? How do you pad a message? How do you do it in TCP, for example, or IP packet? Okay, or at data link layer, right? So there are a number of ways to do that. One way is, of course, define the message length. Okay, and other method is, of course, make it multiple of 128 bits in our case here. But if the last message, the last block is smaller, or last part of the message is smaller than 128 bits, then pad it with the remaining. Okay, so now how do you pad it? Can you fill zeros in the remaining, or can you fill ones? You don't know. How do you know that how long the message is? What you say is zeros, one as padded, that can also be part of the regular message, right? Or the original block. Until you send length information, right? Which you are not doing here. You understand? Then there must be some way. What can be that way? To understand the problem. So for some blocks are known. Say P1 is 128, P2 is 128. Say let's assume the P3 is 128, means that 128 bits means how many bytes? 16 bytes, right? So this is 16 byte. This is 16 byte. Let's assume this is 13 bytes only. So then, while we need to create a block of 16 bytes, so 3 bytes are to be filled in with something. That's the problem, right? Now, if you put zeros, so you say that let's put all zeros, then it's not revealing anything, right? How receiver will know this is not part of the original block? Okay, so the one simple method is that okay. So we're not going to get into details of this because still we have some more part of the lecture to be covered. So basically, let's assume this is 13 byte message. Now note that each is a byte, not bit, right? So this is 13 byte message. We need to fill in with 3 more bytes. Okay, as we said earlier. So this is 13 bytes which are part of the last part of the message, and 3 bytes are to filled. So what we can do is that one algorithm says that to fill the remaining part with bit patterns 3. Okay, so we can fill this with 3333. Of course, 3 is to be coded in bytes, right? But how do you know that this is a correct method? Then you'll have to prove. In comp science, everything you have to prove. Okay, then it works. So you'll find out that it works. Okay, this is one method. So I'm not going to get into details here. Please read it from the book. The method is given here, right? It's also used in, it's called PKCS #7. So basically it's used also in public key encryption. PK stands for public key. Okay, is it So now CBC, AES, CBC is IND CPK secure. Yes, yes. But what is the assumption? That's secure. That IV must be randomly generated. IV applies for the first block. Okay, and then subsequently use that randomness in subsequent blocks. But IV should be randomly generated, should never be reused. What happens if you reuse IV? Then scheme becomes deterministic. And there is no IND CPA security. So let's assume that there are three messages, three block messages, P1, P2, P3, and P1, P2, P4. Okay. So there are two messages, say M1 and M2, and which has the parts of that are P1, P2, P3, and then P1, P2, P4. Now P1, note that P1 are the same here in those messages. Second part is also same, or second block is same, third part block is different. Okay. Now if you use the same IV, so now CBC would reveal when the two messages start with the same plain text block and up to first different text block. Okay, because same IV is there, then some information is leaked by encrypted output of these two. Okay, all right. So now it means that it is not. So we never use, the message is that we should never use same IV in multiple messages, because again it will leak some information. Now you notice that output of these two is similar to output of these two. So now again you are revealing something. So now how the output would look like in CBC mode? This is the penguin. When we say penguin, actually is a file which encodes this penguin, and then we apply CBC encryption AES CBC. Okay, of course there is some key. What we get output, we'll see that comes out like this. Okay, you can't make out anything now. All right. So what we want to achieve, we have achieved a lot. Okay, what we want to achieve is now improving efficiency. Okay, and then more corresponding mode is called CTR mode. Now we notice something from OTP, one time pad. Okay, and use that knowledge. Okay, so we notice that one time pad is secure because keys change every time. But here we cannot change the key, right? Because changing key every time is hard. Okay, then we need to change something else. Like we have seen in earlier case, we added IV. Okay, so here we'll think that can we do something else? And answer is yes. Okay, so this is a normal method. Okay, this is the text that we want to encrypt. We use encryption algorithm, say AES, use key, and you get this output. Okay. Of course, attacker doesn't know the key, so output looks random here. Okay, but it may still reveal some information, right? As we seen earlier. So what we can do is that now we can use this as a random input as a random. Now this, note that this is not the text you want to encrypt. The input to encryption is a random text. Okay, and now the output of that we use exclusive OR with the plain text, or what we say P1, or this is P2, part of the original message. P2, this is P3. Okay, all right. So now let me go back. So what we do is that we use the nonce, one randomly generated input and a counter here. This region we say is a counter mode. And then use the same thing in the second block, okay, or we call it yeah. And how would change the value of the counter? The nonce remains the same, this same, while this is not the same. It increments by 1, and use the same nonce and change the counter to. Okay, now take this input, encrypt it with the key, you get some output. And now note that this output will have some randomization, right? What do you call that? It will not be because the counter value is changing. So basically, we are changing the pattern. Okay, and now we exclusive OR with the plain text and get the ciphertext. Okay. All right. So what do we need to now in order to decrypt it? What do all we need? So okay. Okay, this we have already seen. This is how we define encryption. Okay. Okay, so CI now output becomes okay. EK IV here is this nonce, and then I is a counter. Okay, and then you okay. So when you encrypt this, then you get this output here. Then you exclusive OR with MI, this say M0 in the beginning or whatever. The first part of the message, we call it P0 or M0, whatever. So let's call it M0 here. We get ciphertext C0. Okay, then you take the same value of IB, change the counter value to 1, encrypt it, using the same key, output you receive, which is also of say 8 bits, because here also is 128, because this together will be 128. And then exclusive OR with plain text, you get C1, and similarly here C2. All right. So decryption is similar. Note that the IV should be known at the end, receiving it. So what we do is that now we again encrypt it. Whatever we receive, we encrypt it. Just a minute. Okay. So what we do is that now we use the same nonce, which is available to Bob at the counter value of 0. Append this, and then use this as encryption, and use the key and encrypt it. So this is essentially same as earlier part. Okay, like in encryption. Now note that we are doing decryption here, and then you exclusive OR with ciphertext, and you get the plain text. Okay. All right. So what are we doing here? In both cases, we are doing encryption. Okay. And then here, instead of plain text, we are doing exclusive OR with ciphertext, and you get the output. Now, why we are doing all this? Any questions? Now, of course, mathematically, you can see that this works. This is correct. Although instead of decryption, we are doing encryption as a part of decryption mechanism. We are doing this because now everything can be parallelized, and it has also randomness. Okay, so it can be parallelized. Now note that is there For example, here nonce is known or IV is known, we call it IV. IV is known, counter of course it starts with 0. A key is known, it can do encryption, and ciphertext is also known. So it will get plain text. Okay, let's go to second step here. Second part. Nonce is known because it has been transmitted to Bob. Counter, he can always find out, increment the counter, because this part has counter 0, second part will have counter 1. Keys, he knows the key, so it will encrypt. And then ciphertext is already available. Second part of ciphertext which has come is available, so it can do exclusive or can get this one. Similarly, third one, right? So now output can, the decryption can also be parallelized. All right. So if you now apply CTR mode to Penguin, we'll get this one. So this looks very similar to what we have seen in earlier case, right? This case here, just let me go back. Here in CBC case, right? Okay, exactly similar. I mean, for naked eyes, of course, there will be some changes inside, right? But what we have achieved is also parallelism. Okay, so speed is also here. So what we have studied today is CBC mode. We started with ECB mode, which is nothing but simple concatenation of output. Then we have come to CBC mode and then CTR mode. All right. Now we can see that this is not absolutely authentic, because Mallory can also change the text. Okay, so Mallory can tamper with ciphertext, which is not guaranteed to, which we are not guaranteed to detect it, right? While confidentiality is there, but not integrity. Somebody in between, it's called man in the middle, can always change the text. Then how Bob will know that the text is changed? All right, so that's all. Okay, any question? Sorry, I've taken some extra time. Please go through the text and you learn it. Okay, and those who have missed the earlier part about assignment, please go through the assignment that I've sent. I have modified it today again, added few more things. And then if you don't understand anything, please let me know. Okay, or ask your TA. Okay, all right, thank you.